So let's go ahead and we're going to do our first example for a Z-interval. And let me start the slideshow. So suppose scores on an exam in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives a sample mean, which is a sample mean score, of 69. Find the confidence estimate for the population mean exam scores, which is the mean scores for all of the exams. So you're probably confused with all those words about what we're looking for. So I don't know the population's mean, but I do have a population standard deviation that's probably been known for a while. Usually standard deviations for populations don't change that much. So from here, I know my population standard deviation is 3. I know they've done a sample of 36 scores, and from those 36 scores, they have a sample mean of 69. They want to find a confidence interval to say, okay, the scores are going to range from a lower bound to an upper bound, and it's 95%. So as you see below, I've put in that the sample mean is 69, population standard deviation is 3, sample size is 36, and the confidence level or confidence interval is 95%. So from there, I could solve it by hand. And if you see here, I found everything to solve it by hand, but I really don't want to do that. Takes too long and it can be difficult because you have to know the critical values and you have to do math by hand. So I'm going to show you how to do it in Minitab. So I'm going to escape out of here and I'm going to go to Minitab. So my first thing to do is I'm going to go to basic statistics and I'm going to go to one sample Z right here. And it's going to bring it up. Since I'm not using any data, remember the problem gave me no data to use, I'm going to click on this little down arrow and do summarize data. And it gives me a different screen. So remember my sample size was 36, my sample mean was 69, and my known standard deviation is 3. This known standard deviation is the same thing as saying the population standard deviation. I'm not going to click anything else. I'm going to hit options. And here, remember, I've got a 95% level of confidence. For confidence intervals, you always want the not equal sign. And that is because this is a two-tailed test. Why? Because you want a range of what the scores can be. So that range means I have a lower bound and an upper bound. So that makes it two tails. I hit OK and I hit OK. And look, I'm given information. I'm going to make my screen bigger, hopefully, so you can see it, but it's not. So what does this mean? Again, I ran a one sample Z. I have a sample size of 36. I have a sample mean of 69. Don't worry about the standard error, the mean. But here is my confidence interval. The lower bound, which means the lowest number, is 68.020, and the upper bound is 69.980. So that's great. Minitab did everything by hand. So let me go back to my PowerPoint. And if I look here, it gives me basically the same thing that I got in Minitab. So let's interpret it. And here are the directions in the PowerPoint if you need them. So I can estimate 95% confidence that the true population mean of exam grades is between 68.02 and 69.98. Again, my lower bound is 68.02 and my upper bound is 69.98. Right? So what I'm saying with there is if I'm looking at ranges for the scores, I can say I'm 95% confident that the exam scores are going to fall between 68.02 and 69.98. What's going to fall between that range? The true population mean. Again, I'm using that sample to see what my population would do because I don't have my population mean. Here's a way for me to estimate it. All right, my final step. I'm given those two things from Minitab, lower bound and upper bound, and then I can find the error bound margin. So I take the sample mean, which was 69, and I subtract the lower bound from it to get 0.98. Or I take the upper bound and subtract the sample mean to get 0.98. Again, you can do it either way. They might be slightly different. So when you're doing the homework and the practice problems, they might be a little bit off, but as long as you're in the ballpark range, you're fine. So for this problem, the error bound is 0.98.